All right. Hello, everybody. Welcome to Database Office Hours and diving deep on databases with Nick over here and Randall over here. We're going to spend the next several weeks talking to you about any questions you have about databases, as well as outlining some of the best practices by speaking with some of our thought leaders and experts within the company and maybe even outside of the company as well. Today, we are joined by Joseph. So, can you tell us a little bit about your title, your role, and
Sure.
maybe your history of amazingness at the company?
Sure. My name is Joseph Idzorek. I'm a product manager on the non-relational database team. I've been working on a number of our services from Dynamodb Accelerator, Dynamodb, TimeStream, but my day job now is on DocumentDB. So I've been working on quite a few of our services and everything from the PRFAQ all the way up through launches and pricing and all the other fun stuff. So we've gone through the whole.
So, in case no one's ever heard that term before, we follow a process at Amazon of working backwards. So, there's something called a PRFAQ, and we've talked about this before in presentations, and Jeff Bezos has published this in a shareholder letter. But we start with the press release and work backwards into the product. And that's a very interesting process, and I think it's led to a lot of the developments that we've had over the years for different databases. And our topic really for today is how to choose the right database for the job. And what I'll say to introduce this is that in 2019, dbengines.org or .com tracked something like 330 different database engines. So it's really hard as a developer or even as a systems architect or something like that to know what database you should use for which set of problems. And we're hoping that over the course of this series, over the course of this next several weeks, we're going to be able to answer a lot of those questions for you and provide some real world use cases for those different databases so that you can adapt and take in a schema for how to evaluate decisions about building different applications. So, what are kind of like the core database types?
Yeah, so if you kind of take a step back and how did we get to 2019 and these 340 different databases, one way to categorize them or one way to look at them is to pivot at 90 degrees and look at what are the different types or categories of databases. And I think, for a long time, we only used relational databases, right? That was pretty much the only game in town. They started being developed in the 70s and they're very prevalent in the 80s, the 90s, and the early 2000s as that was, the predominant technology we used.
And one of the reasons I think that they took off like that is because do you remember how big a hard drive was in like 1985?
This big?
No. That's the current hard drives, right? But in the early 80s and even before that, a 5 megabyte hard drive was the size of this table. So you optimized for storage with something like normal form.
Exactly.
And the kind of the crux of things, I think, is that the real world doesn't always fit so neatly into rows and columns.
Yeah, I mean, storage at one point in time became a question of how many of these hard drives can we physically fit in a room, right? And like that would then constrain sort of what your application could even look like. So requirements have changed over time, but some of these patterns around types of data that exist, access patterns, and what those look like from applications, new ones have evolved, but we still see some of these old tried and true sort of systems still extremely prevalent today. So I figure, well, we know that databases are purpose-built here at Amazon, but why don't we talk about some of the different types of data that exist out in the wild, maybe, and how we've worked backwards from those types of data and their workloads to build some of these databases. Like, what are the broad overview of these different services? What are their trade-offs, and what should people think about when they're looking to use them?
Yeah, I think broadly, we see, like 8 large data categories that a lot of these data models and use cases fit into. We have relational, we have key value, we have document, we have in-memory, search as a category, graph databases, and then some of the newer categories that we've had services in now is time series and ledger databases, which is really cutting edge data models where do some pretty powerful things. And I think really the important thing to note is for each of these data models is that they each have their own specific purpose. I think we can all attest that technology doesn't come up and stay, and people don't use it if it doesn't have a purpose and doesn't solve a unique problem. And that's what each one of these databases does. It solves a unique set of problems for different types of workloads and use cases.
Definitely. So, especially towards the tail end of the ones you were speaking about, a lot of the best in slot databases essentially will boil down to really specific nuances, like what are your access patterns or behaviors. But for a lot of people, they still are asking the question of, should I go relational or non-relational? What are the trade-offs between them? What are even the differences? You know, like where does someone start when they're trying to think about, okay, I have data. What are the first questions I should ask?
Sure. Yeah. I mean, the first question is, what is your use case? What are you trying to accomplish? And what do those data access patterns look like? It's always work. And then to, Randall's point, we always work backwards, right? You always want to work backwards from what your use case is, because you say like, hey, what I want to do is like build a recommendation engine. That's my use case. Then you say, okay, well, let's actually work backwards from the use case, not the technology, and say, okay, well, if you have a recommendation engine, what types of questions do you want to ask? Oh, you want to know, a directed graph question. You want to build something that has associated values. Then you say, okay, well, what technology enables me to answer those types of questions or build those types of experiences for my customers? Versus saying like, hey, this is kind of how we used to develop, right? We used to say like, hey, I'm going to use a relational database and I don't really care what the use case is. I'm going to jam it into this particular technology. And I think we're seeing developers do the exact opposite that now of saying like, hey, I have a log analytics use case, or I have an observability use case, or I have, a financial or transactional processing use case, and then saying, okay, well, what are the technologies that enable me to provide the right experience for that?
So let's quickly enumerate the categories. So we have relational, we have in memory, we have key value document, we have graph, time series, ledger, search, and then kind of off on the side we have the analytics and data warehousing solutions. Mm-hmm. So if we dive deep on each of the solutions that we provide for those broad categories, what would we have on the RDS side, we have, say, both, the most database engines available, MariaDB, we have MySQL, we have Oracle, MySQL Server, we have, what else? Postgres. Yeah. We have Aurora, which is kind of that cloud native reimagining of databases. And, if you were to build a database as a cloud native situation, how would you do that? And on Aurora, you can build in like the MySQL version or the Postgres version. Then you hop over to in-memory data storage. You get Elasticache, you get Redis. Then you can go over to graph databases and you get Neptune. That's right. And that allows you to reference things in both Gremlin and Sparkle. Then you have, we have a comment from Twitch from Mittens the Killer Bunny that says flat file databases. So S3, the interesting thing is with S3 Select, you really do have flat file databases. You can run a query on compressed JSON or compressed CSVs and stuff like that.
I would argue S3 is probably the largest NoSQL database nobody ever talks about.
And then with Athena, you can, create those tables and the multitude of things available. We even have some newer offerings, things like time series and things like Quantum Ledger Database. And I don't even think I covered Amazon Elasticsearch, and what else did I forget? DocumentDB, DynamoDB. Those are kind of the NoSQL offerings. And I think, we offer a lot of managed versions of these databases. And to go back to your point, Nick, of why do we do this? A lot of that roadmap is customer driven. So maybe it would help for us to see some kind of, visual demo of how these different databases can be used together, so that we could understand why customers are building on purpose-built databases, why customers are choosing different databases instead of throwing everything wholesale into this relational database service. So maybe we can show your screen here.
Yeah, that'd be good.
Yeah.
So I think when we all look at applications, we use these all the time, right? We use these on our phones. We go to a website. It all looks very put together to us, right? It looks like one coherent experience. And I think that's what everybody's, when they build an app, that's what you're trying to achieve for your customers or your end users. But when you think about like how this is actually architected behind the scenes, and you have a lot of, latitude in saying, okay, well, I have a bunch of different use cases here. We have product catalog, and we have a shopping cart, and we have a bestseller list, and we have product search and a recommendation engine and a leaderboard, right? Those are all very distinct use cases. If we look at those use cases and we say, well, we're probably not using the same database in every single one of these use cases behind the scenes. This isn't all being just jammed into one MySQL database, right? When we think about architecting for scale and functionality and performance, we want to make sure for each of these use cases, we're going to pick the right tool that's going to help us, provide our customers with a really great experience, but also help us grow, scale, make it something that's sustainable that we can run this and continue to build on it. So if we look at this particular, I think we're all kind of familiar with what this web application might look like, right? This is kind of a bookstore.
I can't imagine a company that would have a bookstore online.
Small online bookstore.
Small.
They like orange. I'm a fan.
Yeah, so I mean, it's it's kind of something that's pretty tangible. If we look at even something like, hey, what would be, if we're just going to store the metadata for something like a product catalog, what would be the different options or what would be the different data stores that we could use that for, and think about what would that data choice be. So we work backwards from that.
In traditional relational database form, you would have an authors table, you'd have a books table, you'd have a users table, you'd have some set of foreign keys relating those, you'd have an orders table, you'd have all of this stuff. And that actually kind of fits the relational model to a degree. But then when it comes to rendering it all, you write these complex queries to get everything to show up in the fashion that you want, and to spare your developers from having to write these absurd queries with n number of joins, you end up building an ORM, and that ORM is yet another version of some mapper over a relational database, when you could have just done something like this with Dynamo.
Yeah, I mean, I'm glad you brought up ORMs, because I think when you look at kind of the evolution of purpose-built databases, for folks, an ORM is object relational mapper, which JSON became very popular in the data tier, right? And then people said, okay, well, I have these objects in my data tier and I want to persist those to a database, but they don't map naturally to rows and tables in a normalized schema.
Sparse schema. And
so how do we make this easier? I think folks that have used ORMs, they work really great until they don't. And when they don't, then you kind of have these challenges. And we work a lot with developers, and we troubleshoot some of these scenarios. And when you bring it all back together again, it looks like a document, right? And it's like, okay, well, there's a whole class of databases that are just purpose-built just to handle documents, to make this transition between here's how I'm storing objects in my application tier, and here's how I can make that easier to persist that and store that in my database. To reduce that friction.
So before we launch into this, I realized some of our viewers are coming directly from the Dynamodb stream, and some of them are joining just now. So maybe we could launch into a broad overview of what Dynamodb is.
Sure. Well, Dynamodb is a key value store. I mean, it's.
I know you were about to say purpose built.
No. So Dynamodb is so if we kind of walk back and why we built Dynamodb today, or why we built it in 2013.
12. I don't remember.
I was really motivated by the fact of, there's a really good example of overburdening a relational database beyond its intended purpose, right? There's a very public story in 2004 where Amazon.com had some issues in December, which is a terrible time for a retailer to have a problem with scaling a database. We looked at the access patterns for how we were actually using that relational database. And most of them are primary keys, right? That's a key value access pattern. A bunch of smart people went off, wrote the Dynamo paper, which was really the genesis for DynamoDB and Cassandra.
And a bunch of other
and a bunch of other technologies. And they really looked at, worked backwards from here's how we're actually using the data, and here's a technology that can solve that problem.
And it was also a kind of an understanding that the formal constraints that we had placed on ourselves from this previous era of, we need an exact acid, we need exact, consistency, and we can't have replicas, everything can only scale up. It was kind of a realization that many of those constraints were not realistic, and we never really depended on them in the first place, because the application wasn't even able to take advantage of those constraints.
Yeah, I mean, ultimately, at the advent of SQL and relational databases, this made it really easy for us to be able to take data that already fit that model, but it also had the unintended effect of us trying to take all of these other types of data that may not necessarily fit relational databases, but we crammed them in there because that was one of the best tools available to do that. And so it was this weird time where people start to think in terms of the tools they have as opposed to just what is sort of put forth in front of them. But DynamoDB really changed the game with regards to that, with sort of blowing the gates open, with making a non-relational sort of option or alternative for it.
And even now, you can sort of have relations. You can write transactions across multiple tables, and you can join these things together in an application level fashion. But very quickly, for those of you who have never heard of it before, DynamoDB, you have the core concept of a table. This might be very familiar for those of you coming from the relational world. Within that table, you have a primary key, you have an optional sort key, and then that primary key is the partitioning key. So I probably should call it a partition key and not a primary key. That sort key is optional. You can use that to search within the partition key. Then you have a set of attributes, and those are sparse attributes. You don't need the same attributes in every column, and they can be of different types. From there, you also have global secondary indexes. And the way that you provision DynamoDB is you don't think about servers. You don't have to worry about provisioning any servers or maintaining any servers. Your access pattern is over an HTTPS API where you say, hey, here's my query. I want you to run it and then send me back the results. And you do this over the network, really. You're not using any kind of like custom drivers or having to do these like complex JVC connections and connection pooling or any of this other like old school stuff with like proxies and bouncers. And you just say, hey, I want my data, please give it to me. And then the service responds. And you're metered on that, you're priced on that in terms of read capacity units or write capacity units. And those correspond to, in kilobytes of access, and you use those per second. And the cool thing about this is that you have a particularly write-heavy workload, then you can provision more write capacity units. If you have a particularly read-heavy workload, then you can provision more read capacity units. And if you want auto-scaling, click a checkbox or you turn it on in the API. And then if you don't want to deal with any of that capacity management at all, you can just turn it into on-demand requests, which is another pricing model that says, I'm just going to pay per request to the database as opposed to paying for this in number of provisioned write capacity units or read capacity units. And that is a very brief summary of DynamoDB. There are a large number of other features like streams and all kinds of other good stuff that maybe we'll have a chance to talk about.
I think we will. But riddle me this, though. What fundamentally makes DynamoDB more scalable than, say, like a relational database? Like, what is it? How do we access the data? What is it, the architectural underpinnings that would allow us to go beyond and do things that would go beyond what we previously had at our disposal?
That's a great question, and I think that you're the perfect person to answer it.
Trying to get you to answer that one. No, I mean, so when you have a key value access pattern, you've made an assumption about the data pattern that really allows you to be able to do some more flexible things in the database. So if you're just doing key value lookups, you can scale that data horizontally. And that allows you not to scale up, but to scale out. And then there really are kind of boundless limits on the size and the amount of write and read throughput that you have. But you've also, you're also changing the way that you're accessing the data. But I think if we use like this example is kind of a driving point.
Go back to your screen here and continue.
Yeah, so I think we kind of I think we kind of go back and we say, okay, well, let's just say we're going to access the data for, these particular books that we have here. It's a pretty simple data model. So let me pick.
So this is like a global unique ID. Is this generated by Python? Okay, sorry. I recognize the UID for it.
No hard questions.
Taking one step back though, what are we looking at right here? So we're looking at
we're looking at the product table that actually is supplying the information or the metadata that shows that displays the cookbooks on our particular website, right? So this is a books table, and we can kind of go back and we can kind of look through all this and let's just pick we'll just pick one of these and look at the schema. Right, so it's pretty simple, right? We have an author, we have a category, we have of course, right? We have a string to an S3 bucket that's going to hold the image for that particular book, and then there's going to be some type of name, a price, and a rating, right? And this all works pretty well in a self-contained document, right? We have a unique identifier, so if it has enough cardinality, it scales really well horizontally. And let's go ahead and just like create a new, change this book a little bit, and let's pick Duluth, right? Duluth, Minnesota, from Minnesota. So spaghetti recipes from Duluth, Minnesota. I was curious
where that one was coming from.
Everything is cheaper in the Midwest. And it's also excellent. All right, so we will save this. So we created an item, and we can access that through the key, and it provides a really nice way. But the nice thing about this architectural choice is I can scale from, I don't know how many, 70 items here to 1 million without having to think about re-architecting my database, right? And that provides a really nice, flexible, scalable data store for this access pattern where, I know I can go from, I can 10x my business or my platform on this without having to think about making a different technology choice.
One other kind of shout out I have for Dynamodb here, I think we released a number in one of our shareholder letters several years ago that up to 100 milliseconds of latency can correspond to a 4% decrease in sales. So it was, I might have those exact numbers wrong, but it was something along those lines. And one of the advantages of DynamoDB is this feature called global tables. So you can bring your data closer to your customers in a multi-region, multi-master environment. So you can have your tables kind of located in the region closest to your customers, and which makes rendering this page significantly faster. And then on top of that, you have DAX, which is
yes,
your baby.
Yes, that was one of the great things I got to work on. But yeah, actually, there's a lot of, like Randall travels a lot, right? When you get off the plane in London, you don't want to spend the latency of your app, have to incur all that latency to be able to use the apps on your phone, right? You expect that experience in London to be the same as the experience in LA, right? That data locality matters.
Yeah.
That's slow.
And we already have services like CloudFront that help to distribute static assets globally into the different regions. But for databases, a bit trickier, but having that closer to reduce latency is extremely important.
And I didn't mean to throw you off there. I was just thinking about that as you were walking through, and I was like, we have some global tables.
No, it's a great point, because when you think about hey, how are the applications that we used to build in the 90s different than the ones we did today, and scale,
latency.
Global accessibility, how many people are going to suffer through 400, 500 milliseconds for a page to render, right? We think the internet's broken at that point, right?
I
It's
know,
frustrating.
It's I can hear the dial-up modem sounds in the background. But seriously, when you talk about scale and scaling to 100 million items, there are plenty of web applications, even startups, that have hundreds of millions of items, because
For sure.
Back in the 90s, if you wanted to build a website, it was like, oh cool, I spin up, I bought my server, I put it in my office, I plugged in the Ethernet, and now I'm good to go.
That's right.
And in 2019, you can put your website on Product Hunt, and then overnight you somehow have 10 million users, and those become daily active users, and you have millions and millions of records. And you're not talking about gigabytes of data. You're sometimes even not talking about terabytes of data. In many cases, you're literally talking about petabytes of data that you're dealing with.
Easily.
And then instead of millions of requests per second or hundreds of thousands of requests per second, it's hundreds of millions of requests per second. It's a much different world than even just 10 years ago.
Yeah, I mean, I think one of the big customers for DynamoDB is Snapchat.
Right.
I mean, think about what New Year's Eve looks like for them. You mean every single time zone, 24 hours, everybody's picking up their phone, and they need a database that can scale to be able to handle those types of workloads.
One of the we had a reInvent talk about Snapchat and DynamoDB back in 2017, or was it 2018?
Probably 2018.
Well,
maybe.
Either last year or the year before, Snapchat came on stage at reInvent and talked about the way they use DynamoDB, and they brought up New Year's Eve, they brought up the World Cup, they brought up giant sporting events and things
World
like that.
Series, when the Cubs won the World Series. I mean,
Did they?
Well, no, I think so. Yes, for surely. But those are monumental events that are unplanned, that if you have to provision your database for a high watermark, that's a tough thing to be able to do.
So before we move on quickly, I've got another question from the chat from Sivafen. So question is, what is your approach in the scenario where you start using DynamoDB and later on need to grab data from different tables? Is it recommended for this use case? And does it perform well for these types of multi or cross-table searches?
Yes. So DynamoDB supports transactions across multiple tables. So if you essentially you grab a context, you grab a handler, and you say, hey, handler, I would like to perform this transaction on this many items. And if I'm not able to complete that transaction, please yell at me and give some useful error back to my development environment. Then when you go over to the do you need to talk to different tables, I was recently on Twitch with the Twitch dev team. So Matt Auerbach from the Twitch dev team and I, we built a multi-tenant polling system that uses a couple different tables across DynamoDB. So one is a DynamoDB table to track users, and one is a DynamoDB table to track different polls and different options within those polls. And you can join those together. What I will say is I came from a relational world, and I then went on to work in the document world with MongoDB, and it took a little while for me to really grok the DynamoDB model. So what I would recommend is we have another episode in a couple of weeks with the amazing Rick Houlihan, where we will walk through, who speaks, by the way, at about 95 miles per hour. So we're going to, if you want to watch the episode, I can also encourage you to play it at half speed. We're going to talk to him about specifically how to model data, even across multiple DynamoDB tables. And I think that episode is really going to clarify a lot of the modeling questions that people have about DynamoDB. I will say that I've been using it for several years, and I'm really starting to be able to manipulate the DynamoDB data model in my head now, and I feel like I'm getting a lot of the schema decisions correct on the first try, whereas in previous years, I would have to really think about it for an hour or two to make sure I was building the right model. The good news about that, though, is if you get it wrong, so long as you get it wrong early on, it's really easy to just create another table and then write some script to move everything in. Even if you have millions of items, it's not like a huge lift and shift effort. It's just, okay, cool, let me transform it.
Yeah, so on the topic of choosing the right databases, like even giving a certain set of data, depending on your access pattern, it may make sense to model that in a different database.
I'm glad you brought that up. So I think if you look at this and say, okay, well, we just made this book, Duluth Spaghetti, and we can kind of scroll down and find it, but that's not really how people search for this type of data, right? You're going to go up to the search experience, and I'm going to type in Duluth here, and I'm going to search for it that way. But that's probably, so when I think about that data model though, that type of full text search, right? I didn't put in an exact key. I didn't put in, I put in something that was partial. That's a different data model, right? That's a different tool that is purpose built for that. And for that, for this particular database, or for this particular use case, I chose the Amazon Elasticsearch service because it's really good dealing with use cases where I'm going to throw something in search, in the search box. I don't actually quite know what I'm looking for, but I want the database to actually come back and say, like, here's what I think you're looking for. Let me make a recommendation for you and return that result set. And that's a totally different way of storing and querying data than a key value access pattern where you're doing very specific lookups. This is much more fuzzy.
Yeah, and so to touch actually on like some of the domain specific problems that exist in search, you have things like stop words. You have things that people use that may be like conditionals, like and or. There are also times where you don't know exactly what you want, but you can think of a concept that may be semantically similar. And so how does Elasticsearch basically improve that from database alternatives like key value store obviously would only be exact, but like what is really possible here under a search-based database system?
Yeah, so I think we're all very familiar with this use case because I think we're all pretty proficient in going into search engines, right? And saying like, hey, I don't know all the words I'm looking for, but I think I can describe enough that will get the results back. In search index, they're built on an inverted index, which is a totally different way of storing data than a B tree or which we use in relational databases, or a key value, which we use in Dynamo. And it's really good for being able to, there's built-in functionality that'll actually score your search versus the results and actually provide you back kind of a ranked list of scored results. And you can tweak that every which way you want it, but it actually makes building these types of use cases a lot easier on developers because that functionality is pushed down into the database. You're not building that in the application tier after you get back a result set. You're pushing those, you're pushing that functionality and that processing down into the database. And these data structures are optimized for these types of queries. They're a lot faster than trying to do a regex search on a different type of database.
For instance, while a lot of different databases will support regular expressions as part of their search parameters, sometimes they can't optimize for prefix matching, they can't optimize for suffix matching, or there's some caveats, like if you use any, like let me match this wildcard in the middle of another wildcard, your query explodes into this n squared kind of probability, or big O, and you don't want that. So the really cool thing that kind of libstimmer, Lucene, Solr, Elasticsearch, that all of these things do is they have an understanding of the search space. And what that means is they understand the English language, or they understand the language that you're searching in, and then they also understand a lot of the keywords that you're searching on. This lets people build faceted search engines, which you could also do in DynamoDB with that category search and things like
Sure.
that. Although that would be a table scan, so you'd have to really store the aggregation, which might be a good point to bring up in a second.
Yes.
Sorry. I didn't mean to jump ahead
No,
of you
that's
there.
good though. Good foreshadowing.
So the cool thing is, if you have a word like traveling, you can get the root of that word, the stem of that word, travel, and then any of the variations of the word traveling or travel could be used as part of the search parameter space when you're looking for those things. And that's done at index time. It's done at the ingestion of the data. It's not done, at the time that you're searching. So you have this fast inverted index where you can go and say, hey, okay, cool, here are all my results.
Yep.
And Elasticsearch also supports some pieces of document storage. So you can build a lot of really complex searches that if you teach someone a basic query language, like I want to find everything by this author, and this is a required field, and this title, and it must have these words, or it must be rated 5 stars. And you can build all of that in Elasticsearch in, 45 minutes.
Yeah, it's incredibly powerful for those use cases, and you're using the functionality of the database. And I think that's a big key, is to not reinvent the wheel in your application tier, but try to use the functionality that the database was built for and been iterated on for multiple years to optimize for those use cases.
So maybe we can go back to the demo, and I'll stop foreshadowing.
Sure. No worries. No, I think, so what we did there is kind of interesting. You should be asking yourselves, like, well, Joe, you wrote to a DynamoDB table, but you just told me you queried Elasticsearch. So how do you use two databases together, right? That becomes, it kind of becomes a question of like, hey, if you're going to use multiple databases in a single app, how do you transfer the data back and forth between, different applications? So one of the really nice features on DynamoDB, and I'll create just a new table, and just to Randall's point, we'll just call this product Twitch. When we create a DynamoDB table, we specify the primary key, right? This is how we access the data. So we'll create this table as a dummy table. And one of the really nice features about DynamoDB is called streams. And streams is a queue that you process. So every time I write or update or delete an item into my DynamoDB table, it gets put on the queue. And then I can read from that queue to say, write to S3, or I can write it to Elasticsearch. So I'm gonna go in, and I already have a table set up here. So I'm gonna enable streams pretty quick, right? Some options.
And the options, I think, are very interesting, because you can say, I only want the keys, in which case your application can go and look up whatever additional data it wants with like some query filter. Or you can say, I only want the new stuff, or I only want the old stuff. Or you can say, hey, I want the change. I want the diff, basically.
That's right. So we can enable streams, which is pretty quick. And then we can go to triggers. And triggers are really nice. This is a way of being able to do asynchronous processing on our content. So every time something, I already have a Lambda function created. We won't get into this in this talk, but I can say, hey, a batch size of 1, which I have for my demo, saying every time something gets written to this queue, I'm going to kick off this trigger, which is a function that knows how to process and write to Elasticsearch, and I can go ahead and create. And that provides a really nice way to do asynchronous processing between my product table and my search. Because if I think about it, my product table, I need that to be, very consistent.
Canonical
right?
resource.
Yep. But if my search is maybe, 100 milliseconds behind my product table, that's perfectly fine. I don't want it the other way around. So it's a really great way to keep those two data stores, and then be able to leverage the functionality and the purpose of each of them. Right?
Yeah.
So there's two use cases.
So, when it comes to a small e-commerce site such as this,
Yes.
Searching by terms that you may already know are one very valuable way of finding that. And so we talked about Elasticsearch, we talked about storing the data in DynamoDB. But one other thing that's really common is, like, let's say I went to go buy a book about spaghetti.
Yes.
What may I want to buy with that,
Yeah, you might say, like, who else, bought a book about spaghetti? And what other things did they purchase, right? And those become very valuable for not only building the website, but also provides you a lot of value and context. Is saying, well, I'm interested in this book, but if you're interested in spaghetti, you might be interested in meatballs and garlic bread and some of these other books. And it's really useful to know what other people have purchased if they've purchased this book.
Exactly.
So if we look at that as a use case, that's really a recommendation engine.
And there's like a lot of work from like the machine learning side of trying to predict what people may want. But ultimately, when you just have a lot of users and you have the behavior of all of them, we can still just simply model the frequencies of all of these different things. What type of data does this really represent, or what type of model does this fit best under?
So these typically fall under a graph database or a graph model. And for me, Nick, I like to visualize these things. Like I'm a visual learner, so when I get to, I don't know. So let me just kind of show you, like I've built a graph model for this to make kind of a little bit easier to understand what this looks like and why this, how we tie this back to the use case. So this is a visualization of a graph for a products. And if we look at this, there's kind of a couple things to note here. When we look at a graph model, the circles are called vertexes, and you can kind of think of these as nouns, right? These are our books or our categories or our people. And in this particular example, these light blue circles are our books. These dark blue circles are our people. And then the things between them are called edges, right? And these can be directed, and they can actually have properties that we can query. And this is what makes graph databases unique versus a relational database is that, the relations are really the first class object in the database. Not only do they, provide, context between things, but you can actually query them and attach, metadata and attributes to them, and they can be something that's very powerful to be able to query. So if we look at this, we start asking questions. So if you think about our use case, we say, okay, well, I have this book, but I want to know who else purchased this book, right? Let's go from this graph. So I know there's a few other people that purchased this graph. And then I want to know what books they purchased, right? And then I want to return that back. That's my recommendation engine, right? I want to know what are the books that other people have purchased, and how good are those books? Maybe we should, rank it by descending order so we only return the good stuff.
And the really cool thing I think to point out about graph databases is so you could model this in a relational database.
For sure, 100%.
And people have done
They have done it.
In fact,
I don't know why you'd want to, but you can.
Well, so actually, before we put that aside though, why would you not want to put this in a graph in a relational database? Because obviously, it may be intuitive where you have a small amount of people, a small amount of books. You want it to maybe you just have a column for the relationship between each of the two objects. It's a 0 or 1. That makes sense to people. But why does that not work at scale?
This actually segues directly into a question that we have from Mittens the Killer Bunny, which is a great username, by the way, on Twitch, who is asking, what are some anti-patterns? When would we not use a certain database for a certain job? And I would say the reason you don't want to use a relational database for this kind of query, for this kind of access pattern, I think it's fine to model this in a relational database for categories and all these other things if you really want to. There's, as your items grow unbounded, that might not work. But if you have a finite set of items and you know that they're going to fit within that relational model, sure, throw that into a relational database. But when you think about your access patterns, when you think about the fact that you want to drive recommendations from that vertice graph, you're going to end up building several sub tables that are double foreign key relations upon double foreign key relations, where those are representing the edges of the connections between the different tables, and then those edges are going to have properties themselves, which makes writing a query about that a specialized, it takes a special human being to be able to, explode their mind into this set of tables to be able to write the query. So it's really about agility, development time, and access patterns, because you get better performance out of a graph database that's optimized for these kinds of traversals instead of trying to throw it and shoehorn it into this relational model.
Yeah, and you start talking about recursive SQL queries, and then you're doing functional testing and unit testing and SQL. And it's one of those things is that really what you want to spend your time on as a developer is building a graph database plus on top of something, or, to be able to answer a question, say, in Neptune using Gremlin, it can be something as simple as one line.
Look at your screen again.
Yeah.
This is really fun for me because so what I will say is, let's show the Gremlin query first, and then I'll do my spiel.
Before we look at the Gremlin query, let's just readdress what the goal of what we're trying to do here is. So we have a graph database. We have vertices, which are people and books, items purchased,
Circles.
and then we have the relationships or the edges, which are these lines. And here it's just purchases, but we can imagine this could also involve reviews or like return to the item, lots of other things.
Yeah, so we have people know each other, we have things belong to categories. Yeah, there's all kinds of different relationships that we can model between all of these, which help us, form different complex relationships.
Yeah. So right now we imagine that we're on a page for a product, and we want to say that okay, for a given user, we want to query like what are the most commonly bought other books that people who bought this book had, right? So given that is the context, like now let's go into examining the gremlin query.
So let's look at this, right? So we would start off and we would say, hey, we have our graph, and we're going to give a particular vertex. This is, book 34.
Book 34.
So we'll start off as book 34. And we want to go in and basically, if you kind of think about this visually, you go in and say, who purchased this book? So who are all the other people that purchased that book? So that's a directed query in. And then, if we go out from those people, what are the other things that they purchased, right? So that kind of gives us, here's this book, who are the people that purchased it, and what are the other books that they purchased? So it kind of gives us that second dimensional information we're looking for. We want to remove ourselves. We don't want to return the same book we just purchased, right? That's annoying. Remove any dupes, and then we want to order descending by the rating. And if we, and that produces a really nice kind of clean result set, then we can then use to be able to supply our web page. But the nice thing about this is this is pushing the functionality down into something that is built to handle these specific queries. So functionality, performance, and scale. You're not going to have to compromise it on it, and you're not going to spend your dev cycles trying to figure out how to do recursive CPEs in a relational database.
Yeah, and I think developer productivity is really important, right? Like, I think when it comes to any tool that you're trying to select for a job, you sort of have two major factors. You have how productive can my developers be with this tool, and how proficient or efficient, and that can translate to cost and speed and so on and so forth. And so at the point where there are people out there that build these algorithms or these search structures and storage structures to optimize that, how can we now create different query interfaces to be able to enable our developers to be productive, right? And so when we talked about our business use case of describing how we want to recommend items, it was kind of just like three logical steps. And so typically in a relational system, you have these nested queries. It can become extremely inefficient very quickly if you have something messed up with it. Yep. Not logical to debug or try to write these, but in a graph database or in a graph schema, this actually becomes really straightforward.
Yeah, it becomes very intuitive, especially writing these queries. Once you have the visualization, that's the purpose of what it was done for. And it's not even just relational. I mean, if you tried to do this in a document store, a key value store, an Elasticsearch, it's not the purpose for that. You can do it, but it's not the purpose. So you're going to spend a lot more time trying to accomplish that.
I think a couple people have some questions about what Neptune is.
Sure.
So graph databases, they are optimized for storing and querying vertices and edges. And those edges are typically rich edges, so they contain data not just about the fact that the items are connected, but the type of connection and even metadata associated with that connection, like the date that it was made on. It's used for modeling everything from social networks to financial data to
fraud detection, life sciences, networking. If you think about hey, what does your corporate network look like? That's a really great use case for modeling in a graph. Even just connections and employees, right? HR, and being able to think about who works with who and what projects. These are all graphs.
Yeah, we're trying to understand sort of how a bunch of pieces in a given ecosystem fit together as opposed to just individual properties of one given entity. That's really where graph databases start to shine.
And you can even use it in, not just for fraud detection, but for even more general machine learning and knowledge modeling. So I spoke on stage in Berlin with Siemens Corporate Technology, who is a large user of Neptune. And what they do is they model all of the different deployments of their hardware that they have. And they have these big turbines, and they deploy them all over the world. And they take all of the data about those turbines, where it was made, when it was made, what materials were used, how long it's been in operation, what the type of operations have been. And they build this big graph of all of that information, and they can query that graph at any point in time to determine where they need to do preventative maintenance, because they can say, okay, based on all of this data, show me all the nodes that are next in line for preventative maintenance. And that allows them to reduce their costs significantly for maintaining that hardware, because they're going out and fixing it before it breaks.
That's right.
And if something does break, they can repopulate that into the graph. So it's a living model. And the other thing that I'll point out is Neptune supports two different kind of modes. It has the Gremlin model that we showed here, and that's kind of the Apache open source Tinkerpop model. And it also supports Sparkle or RDF models. And I find when I go out and talk with customers that RDF is more common than Gremlin. And that's not what I would have expected, because as a developer, I actually find Tinkerpop to be a little more fun to interact with. It's easier to write the queries, it's easier for me to think about, and it's not XML. So I promise I'm not biased at all. So then when you get into RDF, it's very much XML based, and the queries are, select, node query. It's a remnant of SQL almost. And the reason people are using these RDF models, and this was a realization for me, and it makes total sense, and Siemens does this as well as a number of other customers, is that you have globally unique identifiers across multiple different data sets because they all pull from a common schema. And you can say, hey, different data sets, different databases, I can join these together at my application level. So I can have multiple different graph databases existing all over the world in different, even a different vendor, even a different company, and I can have all of that information pulled together with a common schema, which is a very unique and cool idea. And that's how Siemens does it.
Yeah, it's a great use case. I mean, I think, they're immensely powerful. I think, a lot of the theory for this has been around for many years, and now the technology is catching up with the theory to make this, to give this to everybody as a tool for people to use and get spin up. I mean, with Neptune now, you can, within minutes, you can get going with a graph database and start being able to start modeling some of these relationships and build these experiences.
So we've talked about Dynamodb, so that's kind of our key value to document store. We've talked about Elasticsearch, which is our search.
Yep.
We've talked about Graph. What about, let's say I have a very expensive query that I want to run. You remember that Dynamodb query where I was saying, hey, I have, I'm going to have to run a table scan because I want the top 20 bestsellers from, say, to the category of cooking, or I want the top 20 bestsellers from the category of science fiction. Those are table scans that I could easily over provision and have a bunch of write capacity units. But if I'm only going to run it, a new book is only published, say, like once a day, or we're only adding, a couple hundred books to our catalog per day. So maybe I only need to run it whenever I add a new book. So that triggers my query, and then I can store that query somewhere and view that aggregation. Can you show us this maybe and how you would build that?
Yeah, so the use case that Randall's bringing up is, we don't have to go, most databases are built where we retrieve data from disk. Not every time we want to be able to go do that table scan or be able to do that query again, and we can basically materialize that or store it in a form that's consolidated, but also in something that's just memory, right? If you take the disk out of the database, it becomes 10 times faster. You don't have to do those access patterns. You don't have to do any write-ahead logs, and it becomes really fast. This is where you go from access times of like milliseconds to something like microseconds. And there's a whole case of use cases there with caching and real-time analytics and session state where the data can be ephemeral, right? It doesn't have to be persisted to disk because it could be stored in a relational or a key value table, but you want that access to that data to be lightning fast, right? We want to be able to persist that data, or we want to be able to access it fast without having to read and write from disk. One really great use case for this is a leaderboard. Right? I think our friends on Twitch are pretty familiar with leaderboards, right? If you think about a leaderboard and say like, hey, if I want to show like, here are my top 20 bestsellers, and every time one of my users came to this website, I had to run that query, select star from orders table, group by, order by. That's going to get pretty slow as the number of orders that I have increases, right? That's going to be a crummy experience. I can always cache the result of that in any type of, in Redis or Memcache, or I can also, if I have, use cases that, hey, I want this to get updated in real time, I can use something in Redis, which is called a sorted set, which is a specialized data type in Redis that makes building leaderboards really easy. And why is it? Because it pushes the data down into the database. So let me show you.
Yeah, let's hop over to your screen and see
what that looks like.
So we've got our good old trusty Redis cluster here.
Yeah, so we think about we just went from the use case where I had 3 books in in my leaderboard, and I can query the data, and I can query Redis. I have a sorted set there, and I have the GUIDs as my unique identifier, and then we can see the scores that are associated with them, right? Top item has 126 purchases, 114, 111. Now, every time I access this particular this data structure in my application, it's just basically a key value get from in-memory. That's a super fast query, right? That's millisecond response time. I'm not doing this huge aggregation. And then every time I come back and say like, hey, let's see, we maybe won't do this on the fly. I'm not as good as Randall, right? So if we say like, hey, we want to...
Control R is basically how I write all of my code.
So we say like, okay, well, let's just say like, imagine that somebody comes in and they really want to bump up that last book. We can add a new member and, 20, right? 20 should give us enough. We can increment that sorted set, right? Increases that to 30, right? Now our least favorite book is now our most favorite book. And next time the user comes to our website, if we do a refresh, right? They're going to have that really fast, instantaneous. Now ice cream becomes the top item in our leaderboard, right? And we didn't have to go write that expensive query that did a table scan over all of our orders for the last N days. We just updated an in-memory data structure, and we just did actually a really simple get to produce that.
And for those of you who may not be familiar with Redis, the core kind of capability, you have maybe 120 different commands, or maybe fewer than 100. I don't remember exactly. You have, partitioning or sharding if you want, but it's at the application level. So your driver ends up being aware of that, not the servers themselves. And everything is kept in memory. There's no real persistence. Well, there's Redis dump, which is a persistence layer of, by some definition of persistence, you could call Redis dump persistence, but there's nothing really persistent to disk by default within Redis. And the way that it works is you store things in one of these predefined data structures. They have maps, they have sorted sets, they have a couple of different trees and other kinds of things, ways of representing things. And then on the other side of Elasticache, which is the managed Redis that we have, you also have Memcached, which is another offering that you can use. Memcached is almost always used to front, say, a WordPress instance or a Drupal instance, or you're caching these HTTP responses. Am I going into another thing you're using?
No, I'm just saying like the whole. Just like you bring up such a valuable point. Is the whole world basically all of technology works on a cache, right? Like, could you imagine streaming Game of Thrones from disk, right? Like that's not coming from disk when you watch that on Sunday nights. When you look at a lot of the apps on your phone, a lot of the content is already cached on your phone. Websites, like I don't know if you could get away without using some type of caching these days.
You really can't, especially when you talk about those aggregations, because the aggregations are expensive. Anytime you have to go down to a table scan, I don't care how amazing or good your database is, you're still looking at a bunch of items that you're planning to discard. Right. Any table scan with a filter or any sort of ad hoc analytics job, you can say, hey, maybe that's a job for our data warehousing. Maybe that's a job for our analytics, for Athena, for Redshift, for something like that. But if you're trying to render those results to a consumer, to an end user, that is difficult to do in real time. So by caching those results and accepting like, hey, it doesn't matter if this is 2 or 3 seconds out of date or even 10 seconds out of date, you're going and buying yourself more time on the database side so that you can provision fewer resources and still serve your customers with faster latency.
Yeah, and ultimately, when you just get to a certain number of users, like you will just kill the number of connections your database can have at a certain point. Like sure. We talk about it as like, oh yeah, caching is nice. It's like pretty cool. It has some good side effects. Like at a certain point, you just need it.
It's essential. Yeah.
Yeah.
And when we talk about AWS Lambda and trying to talk to a database, you have to think about the way that those Lambda are going to talk to your database. With DynamoDB, you don't have to worry about it, right? You can have, LOL, let me open, 1 million connections. And then DynamoDB says, okay, fine. And if you wanted to do that with a relational database, you'd have to have something like PG Bounce running to basically create a connection pool. And that's a problem. This is a problem really that we should solve at some point.
Yeah, absolutely, and yeah, it's yeah. That's a good point.
bake that into a product feature request going forward, right?
I think it's OP one time.
All right, so we have a few minutes left before we get to ending remarks. We just touched on Memcache. I just wanted to say a little bit about TimeStream. So Amazon TimeStream, a database that is built around time series data. And so at first glance, when developers are working with time series data, oftentimes it looks pretty similar to something you'd throw in a relational database, right? And
They have timestamps.
exactly.
Yes.
So it's essentially just the data you throw into a relational database. However, your primary key becomes a timestamp. But what we see is that the access patterns, both how it's written, how it's typically read, the orders in which certain parts of the data will become infrequently accessed, those are very specific to time series data. So could you just talk a little bit, Joe, about like why TimeStream came about it and how we've worked on some efficiencies under the hood? I know we'll have an episode later on in the season that really goes into it, but from a surface level, like why TimeStream? Why a time series database?
Yeah, if you look at, if we work backwards from our customers and what they're doing with this, you look at a lot of use cases like click streams and telemetry coming off of IoT devices, mobile apps, sensors on doors, and you look at all of this data, and it's all time stamped, and it's not like, hey, I have a table and one of the fields has a timestamp in it. It's like that is the key dimension because we want to understand how this data changes over time. It's not just the final value, but what was the slope, what was the how did it, I think we've all learned DevOps. And you look at this and you want to understand how it's changed, but we look at data models and you can say, hey, I can look at, relational, a key value, a document store, and it has a timestamp. Does that make it a time series database?
A sort key is not a time series.
When you look at those use cases, and you can make that assumption that all the data that's going to be coming into the database is going to be both keyed with time and also queried over a range of time, you can do some incredibly amazing things with how you store and access the data. You're not trying to make this a general purpose database where you're all of a sudden going to have a key that's now a string, or it's going to be, some other type of, float or an int or something. It's a timestamp. And you can do some incredible things that make ingesting and querying that data incredibly fast. Orders of magnitude faster than you would in other types of data stores because it is optimized for those access patterns. Inserting things with the timestamp, right? If you do this on a B tree, right, the way that we store data in a lot of other data stores, you kind of get contention on that last page, right? You're always trying to write to the last page of the B tree, which becomes really inefficient for being able to do this. Because like if you think about like, hey, I have a whole fleet of tractors and they're writing 1 million requests per second. All the different, information that's coming out about the tractor, the engine temperature, where you planted something, what was the humidity. You have a lot of data and you want to be able to ingest that. So that's what time series databases are for, is when you have time series is this, the primary access of the database.
So there's like an ingestion time and there's an event time, and the way the time series is architected is you actually have 3 different tiers of storage. So at the first tier you have in memory, and this is where you can run a lot of really fast calculations, and then you have policies that will outline exactly kind of how you should age that data out. And I'm going to go very quickly here because we have one last question from Sivafin that I want to get to. The second tier would be on disk, and then the third tier would be maybe magnetic storage or a slower version of on disk storage. And each one of those is priced differently, and you pay for the amount and the number of hours that you store it. And then you query that with a common kind of like SQL language that you're probably used to. Sivafin's question is, what are ledger databases used for? And ledger databases are basically cryptographically verifiable append-only journals that should scale endlessly.
The use cases for those, like why would I use a ledger database? You want something that you can guarantee pushing that down into the database that nobody has modified, and you can go back and verify that, say, the lineage of a car for a DMV record, or like the supply chain for a particular medical device has not been tampered with, and you can go back and verify it. And it's really hard to build that in another database. You can't guarantee that some sysadmin didn't come in and delete a row or do something, beyond. You don't have any tools to do that.
I've been that sysadmin.
Yeah, so that's what this database solves. Or this database solves is that the database actually provides those guarantees, and then you can use, very tried and true math to prove that.
All right, folks, we have just a few minutes left. So what I want to do very quickly, over the next several weeks, we are going to be coming to you as many weeks as possible on Tuesday at noon to talk to you about each one of the databases that we covered today, as well as a few other concepts like migration. We're going to be talking to principal engineers and experts from around the company, and I really encourage you to send in all of your questions. Let us know what you want to know. Let us know what we can tell you, what we can help you with within your existing architecture. Nick, anything you want to add?
Yeah, so we have a few ways you can do this. If you can't make it for the stream time slot, I'm sorry, but we will have these VODs available both on Twitch and on YouTube. But we also have an email address that you can reach out to. I believe that's databases deep dive at amazon.com. You can email us your questions there. We will bring them up here in the streams. Other than that, we also have a form that you can submit your questions through, a schedule. The next episode, I believe, is going to be May 7th.
Yes.
So be on the lookout. Send a follow to twitch.tv/AWS if you aren't already, and you should be notified for when these new streams are happening.
Joe, thanks so much for coming.
Hey, thanks for
Hope to
having
see you
me.
again.
Yeah, Joe,
Thanks,
great
Nick.
seeing you.
Appreciate
Thanks again.
it.
Bye, everybody. See you next
Signing
time.
off. See you around.